Hey there. In this video, we're going to talk about exponential models. Whenever you hear us talking about models, we're talking about applications. We're talking about real world problems, and we're using math to describe or model the behavior of the real world. So one of the most common exponential functions that you will see is an exponential growth or decay equation formula. So here it's written as A of t equals A naught times e to the kt. A of t, that's the amount you have at any given time. Maybe it's a population. A naught is your starting value, or A sub zero could be read as well. So whatever you started with at time zero, that's your A naught in the equation. E is the number E. K is your growth or decay constant. If K is positive, then you're looking at a growth model, population increasing. If K is less than 0 or negative, then you're looking at decay or decreasing population. And then T is your time. Another example of a model with an exponential function in it is Newton's law of cooling. Newton's law of cooling allows you to take an object that's hot and see predict how it cools over time, depending on the temperature of its surroundings. So this function is T of t equals A times e to the kt plus Ts. That Ts is your surrounding temperature, the room of room temperature, or sometimes called ambient temperature. A is the difference between the initial temperature of the object and the surroundings. And K is the continuous rate of cooling. And T is your time with this one. And we're going to do an example of this one just to see how it might be used and how you would solve an equation with this kind of, using this formula. Okay, so a cup of hot coffee with an internal temperature of 200 degrees Fahrenheit is provided to a customer at a coffee shop that is 72 degrees. After 5 minutes, the internal temperature of the coffee is down to 150. Using Newton's law of cooling, write a formula that models this situation. Okay, so we have our formula up in the top right corner there, and we want to start assigning the values they gave us to this formula and see what we can do to solve the whole thing. What we don't have, just at a cursory glance, is the constant K. And so we're going to use the information they gave us to come up with that value. So first off, they gave us the surrounding temperature, the room temperature, which is 72. We can also find A by subtracting the difference of the coffee's temperature and the room temperature. So 200 minus 72 gives us 128. So that's our A. They give us a time of 5 minutes. And they tell us at time 5 minutes, the temperature is 150. So I can use that as a point to plug in and find any remaining unknowns in this equation. So plugging everything in that we have there, T of t is 500, A was 128, T is 5 minutes, and Ts is 72. So I have 150 equals 128 e to the 5k plus 72. Only thing I don't know is that constant k. So I'm going to solve this equation so I can get a general formula that will help me predict, well, what's the temperature going to be after 10 minutes, for instance. So first step, I want to get rid of the 72. I want to isolate that exponential piece of the formula on the right. So I'm going to subtract 72 from both sides. That gives me 78 equals 128 e to the 5k. And then I'm going to multiply by 128, again, trying to further isolate that exponential piece. So 78 over 128, I'm not even going to bother to simplify it, equals e to the 5k. From here, I need to get that 5k. I'm trying to solve for k. I'm trying to get that out of the exponent so that I can solve for it. So I'm going to take the natural log of each side. Now, you might be tempted to take the common log, base 10 of both sides, but because my base on this exponent is e, I definitely want to use natural log here because of that inverse property of logs. The base of my log matches the base of my exponent. So the right side of this equation simplifies to just 5k. The natural log of e to the 5k is just 5k after it all simplifies. So that saves me some time by choosing natural log over a different base. And from here, all I'm going to do is divide by 5 to get my final answer. So k equals 1/5 times the natural log of 78 over 128. And if I plug all that in to get an approximation, normally we would do that in an applied problem and take it out several decimal places. So I get negative 0.0991. 4 decimal places is a good rule of thumb for these. So if I plug that back in with all my information other than the 5 minutes, I get a general formula T of t equals 128 times e to the negative 0.0991t plus 72.